So there's three primary modes of snow transport, and these modes are the same types of modes for the transport of any small granular object like silt or sand or snow. And the classification is a function of the distance from the surface of the ground at which this process is operative. So on the left side over here of this figure, you have processes that are occurring really near to the snow surface, like a millimeter off the top. And we call that rolling. Sometimes that's called creep as well. And as you move further up off the deck, you have the process called saltation, salt coming from the Latin root for jump. So now you have these particles that are sort of bombarding each other and lifting off the ground. And then when you have really high wind speeds up further off the ground here, 10 to 100 meters, you have turbulent suspension. Two other general categorizations for snow transport are a drifting snow, which is, it sort of categorizes all near surface transport, so that includes both rolling and saltation. And then you have blowing snow, which is the stuff that's blowing in your face. That's occurring up several meters off the ground. In order for snow grains to move, the wind speed has to surpass a minimum threshold. And so we have a plot here that's showing you the threshold wind speed as a function of, in this case, the ambient air temperature. So it turns out that the threshold, that speed that's required to lift that particle into the air, is a function of lots of different parameters, including moisture, humidity in the air, the age of the snow. But why? So pause the video for 2 or 3 seconds and see if you can come up with a speculative reason for why you think that's the case. Well, there's lots of reasons here, and I'm just illustrating a few, but as you'd expect, warmer snow is typically stickier. There's more moisture content, which means stickier snow is harder to move into the air, means it needs a higher threshold wind speed. Older snow is typically larger grains. They're rounded, bonded clusters. They're harder to lift off the ground, and that's what you're seeing here in terms of the difference between the aged snow and the fresh snow requiring a lower threshold wind speed. So in terms of the velocity at which snow grains can move through the air, the snow transport rates are proportional to the wind speed at 10 meters off the surface, so that's roughly 30 feet off the ground, which we signify as U10. And the relationship is cubic. So what happens to the snow transport velocity when the wind speed increases by a factor of 4 if the snow transport rate is proportional to the cube of the wind velocity at 10 meters from the surface? Well, if U increases by a factor of 4, 4 cubed is 64. So what that means in practical terms is that the snow transport rate will increase by a factor of 64 times when the wind speed increases only by a factor of 4. So this is a really significant relationship between snow transport rate and the wind velocity at 10 meters. This plot better captures that idea. So we have the snow transport in kilograms per meter second as a function of the wind speed at 10 meters. And this is sort of summarizing a variety of empirical measurements by different groups. But notice that this is a logarithmic axis on the y, and this is linear. So this is a semi-log plot. And so this is illustrating that cubic relationship where the transport rate increases with the cube of the wind speed here. Recent studies have actually used particle tracking velocimetry, which allows you to take a video image and track every individual snow grain in a field of view and assign a particular snow particle velocity vector, which you're seeing here. And so the color coding is this axis, so it's meters per second velocity. This is horizontal distance, and this is vertical distance. And you can sort of see some of these creep effects or rolling effects on the ground, and then you start to see some of the saltation effects and the velocities increasing as those individual grains move further off of the snowbed. Okay, so I have a couple videos here of both rolling and saltating snow, which is on the left, and suspended snow, which is on the right. These are both at the same location in the 10-mile range in Colorado. So you can see both evidence of rolling, creep, and saltation in the left video, and then you can see several meters off the ground snow that's blowing across the frame of the camera here. So what are some of the characteristics of each of these modes of transport? So creep is typically stuff that's moving roughly a millimeter off the snowpack, and saltating is when individual grains have actually smashed into other grains on the surface, other crystals, and kicked them up into the air. And typically the threshold wind speed for saltation is around 5 meters per second when you have really cold, loose snow. So this was up in the Alpine, just around tree line on a day that was sub-zero with recent snowfall, so very loose, not very dense snow. What about suspension? So with suspension, typically you need threshold wind speeds above 5, often even above 10, unless you have really cold, dry, loose snow. You also have to have this condition where the eddy current that's caused by the wind, that upward force, it has to exceed the snowfall rate or the actual velocity of snow that's coming downward. And in general, all of this mass of snow that's moving, this mass transport by saltation and suspension, they tend to load up avalanche terrain in these deceleration regions, which I'll talk about here in a second. So the transport mode is dictated by a balance of a variety of forces, but it also is a function of the size and the density of the individual snow grains. And this is an old figure, but a really important one that shows wind velocity down here at 10 meters. We have 3 different types of particles, so sand, snow, and silt. Silt being the very small grain, snow sort of being in the middle, and sand being these larger grains. And then on the y-axis we have the proportion of up currents exceeding the fall velocity. And fall velocity means the velocity or the rate at which the silt, the snow, or the sand particles are falling vertically down to the ground. And so what it's essentially capturing here in this figure is that as the wind velocity increases, we're capturing a greater percentage of those grains and keeping them in suspension in turbulent flow above the ground. There's been lots of studies to quantify this, which we won't go into great detail here, but a lot of models have shown that you can kind of capture these regions largely based on the critical velocity, which is plotted here, y, as a function of the diameter of the grain. And so you can see when you have really small grains down here, this is a log axis here, so small grains on the order of single microns, then when you hit the critical velocity of wind, you can get these things up in suspension. Below that you don't have much motion, but then as particle size increases closer to 10 microns, we hit a saltation regime, and then we sort of have a balance of other things. And what this is showing essentially is that we don't typically have individual snow transport regimes that are operative. We actually have a combination of lots of them. So that means that when you have rolling snow, you may also have some proportion that's saltating, and then you also may have some snow that's in suspension based on a variety of factors in the complex snowpack and the grain size. More recent models have sort of tried to categorize these even more, and then linked that to the relationship to different surface properties. So the observation of the surface of the snowpack, or what they call the bed form of the snow, as a function of the result of these different types of snow transport. And so this is just another illustration of creep mechanism, and this is all below that threshold wind velocity of 5 meters per second. Then we have sort of between 5 and 8, we've got some saltation mixed with rolling over the surface, causing these sort of ripple effects, and then in excess of 8, we get more grain saltating and more stuff pushing up into suspension. This plot, I think, is a nice summary of all of these effects, where we have the threshold here in meters per second, the wind velocity threshold of that particle, and then we have different domains. And so they're showing down here the creep-dominated domain, so in the types of resultant surfaces that you would observe on the snow, what they call crag and tail, and some of these ripple marks. And then once you start to see saltation as the dominant snow transport, then you start to get these other regimes here. So we have sastrugi, which are sort of these ripple patterns, barcan, barcanoid, and snow wave effects. And then as we get higher and higher wind velocities out here, that's when we start to get snow dune formation. Current studies, as I mentioned, some folks will use particle velocimetry, so looking or tracking individual particles and then using image recognition and tracking algorithms to sort of map the velocity vectors of individual grains. Another way is to look at the surface of snow from the air or from satellites and use laser scanning technology to sort of map the contours as a function of time. And you can sort of use, again, some image tracking and processing to then figure out how the surface of the snow is changing as a function of these external parameters like wind speed, velocity as a function of height off the surface. What's important in terms of takeaways here that I alluded to earlier is that the types of these snow bed forms, or the surface structure of snow, is often mixed in terms of seeing some sastrugi, some pitting, and some dunes that may form. And that's largely because of the complexity of the surface wind and how that evolves over short and longer time periods. And so it can be difficult to look at the snowbed and discern exactly what mode of transport was operative at any given moment in time. These are images that I've captured in the last several years. The question that I want you to answer here, and pause the video, is which direction is the wind blowing in each of these images? So go ahead and pause, take a few seconds, and see if you can answer it. So the image on the left over here, this is a classic image of sastrugi, these sort of wind ripples on the surface of snow, and you can see the ridges that form. And it may originally, when you first look at this, if you haven't studied or looked at sastrugi before, you may be compelled to think that the wind is blowing left to right in this image. But in fact, when you have these ridges, what you're seeing is the undercutting because the wind is blowing from right to left. And as the wind blows from right to left, it undercuts underneath these lips and causes wind to saltate up, or the grains to saltate up, and it undercuts underneath each of these ledges, and that's what causes the rippling. So the image to the left, the sastrugi image, is blowing right to left. The image over here is a really nice one, and it's similar. So this is actually the effect of riming. So this is the deposition of snow as wind is blowing over a surface, and the snow ice crystals are depositing in real time. And in this case, the snow is blowing from right to left, and so you're actually getting deposition on what we'd call the sort of leeward side of these branches as the vapor wraps around the branch and then deposits over here. And in the central image here, it's pretty obvious all of the loading is coming from the right side here. So the wind is depositing down onto this side. And if I were to have a video captured here, you'd see some barren parts of the tree on the left side, whereas the right side is completely filled with snow. So what are the effects of wind on the actual grains themselves? So when snow crystals form in the atmosphere, they, not always, but often they're going to form these more highly symmetric crystals, or these stellated or dendritic crystals like this. But as the wind moves them and moves them across other grains or other features like trees or snowbed surfaces, it starts to abrade those grains and break them up into smaller and smaller and smaller bits until they're unrecognizable from the original dendritic crystals that fell from the atmosphere. The result there is that we get an increase in the density of the snow once it does deposit on the surface of the snowpack, and we have a better chance of cohesion amongst particles because it's easier for small particles to form a cohesive layer, or slab we sometimes call, compared when you have these large high surface area particles that don't actually pack well together like the ones that fall from the atmosphere. So the figure over on the left shows the low density surface snow, and this is dense snow under here, and then we have this wind erosion effect, so high winds, and so that stirs up the surface either through saltation or suspension, breaks up the particles from this, and that results in redeposition of the snow again, and then we end up having a denser snowpack than what we had when we had the original low density dendritic snow grains that fell. And so in this particular circumstance, we're showing snow that fell likely under light wind or no wind conditions was then transported abraded, broken up into small grains, and then redeposited, rather than the wind abrading as it's falling from the atmosphere. Both cases can occur. This is just showing one. And the electron microscopy images show you sort of the comparison of both. So on the left image, you have these highly dendritic crystals that formed under high supersaturation conditions in the atmosphere. And then on the right, you have the crystals as they've been abraded by the wind and broken down into these small grains that are totally unrecognizable. But this illustrates nicely how you can increase the density then of that resulting snowpack layer and the cohesion of these, which in turn can create these things called wind slabs, which are really problematic for potential avalanche risk. So that leads to the question of how does the impact, or how does this process impact the stability of the snowpack? And in this image, this is just an image of a wind slab that's been deposited on the surface of a crystal type called depth hoar. And you can even see in this image the density difference here. So pause the video for a few minutes or a few seconds and see if you can answer the questions. Which layer would you expect to be harder and denser, and why would this be problematic? So the micrographs from the snow loop of each layer are shown over on the left, and so you have these really small sort of abraded rounded grains in the wind slab that pack tightly together, forming a dense hard layer on top. And then below you have depth hoar, which are typically these faceted cup-shaped crystals like this that are often several millimeters. This one is 5 or 6 millimeters. And you can see the abnormal shapes, the asymmetry here, lead to poor packing densities and non-dense layer. And so the reason this becomes a problem is if a human were to load this surface of the wind slab in a vehicle or on their feet or on skis or snowshoes, that dense layer, that pressure could cause volumetric collapse at its depth hoar because it's lower density, high density, hardness, on low density, low hardness, that collapses this layer, and if it's on a steep slope, that slab then will crack and slide directionally to a lower slope angle region, and that's the cause of a wind slab avalanche. Another really important implication of turbulence and wind in snow transport is that snow transport increases sublimation losses. And so sublimation, remember, is the movement of one phase of snow in the solid form directly into gas form, skipping over that liquid phase of water. And that's exactly what you're seeing in this image, and you see this often on the surface or up high on Pikes Peak on windy days. And the reason for this is these very small snow grains that have been abraded are now suspended in the air, and they're very vulnerable because they're not protected in the snowpack or in trees or other features. They're up in the air like this and exposed on all sides to the potentially low vapor pressure surroundings, which can cause the solid to move directly into the gas phase. And this is also true when you have snowfall that falls into trees. So if you have highly vegetated areas, lots of trees, the snow, for the same reason, is more exposed to wind than more exposed to sublimation effects. And this can be really important for modeling snowpack and hydrology in a particular basin or subbasin. So for example, in coniferous trees, about a quarter of all of the snowpack is lost to sublimation losses in trees in the state of New Hampshire. More than 40% is estimated in the Yukon. In Colorado, it depends on where you are. Up on Niwot Ridge, where there's a snow study course, the estimates are typically between 10 and 15%. So what that means is sublimation, or the loss through the tree canopy of snow, is really important for hydrologists in understanding with wind events how the snowpack is changing from year to year, which then affects things like droughts and the ecology of and the health of forests. So this is a slight simplification, but is largely true and has large impact for snow transport, and that's that air moves faster over a ridge compared with movement of air over flat terrain. And the analogy here that that makes some sense is that because that same flux of air must be moved or sort of packed into a narrower band of elevation. You're seeing that in this rightmost figure. And that's similar to if you have a wide meandering river that all of a sudden channels down into a really narrow region, and you start to get white water and rapid flow rates, and that's because the same amount of water is now being forced through a smaller region, and that's because of these sort of boundary effects where you have different parts or regions of the upper part of the atmosphere that constrains how the air is moving. So you essentially have a ceiling here that forces all of this air that came from the valley floor up through a smaller and narrower window, and so you get higher rates, which, as we mentioned before, the wind speed, or actually the snow transport velocity, scales with the cube of the wind speed 10 meters off the surface of the ground. And so if that's true, then that means we get really high snow transport velocities as we move higher up on mountainsides and ridges. So once snow has been transported, what does that do in terms of deposition? Where does it go, and how does that impact the snowpack itself? Well, huge amounts of snow, massive amounts of snow are moved around because of turbulent transport or wind. And one of these mechanisms, or often several of these mechanisms that we described. And the general idea is that we have wind or turbulence that accelerates, typically as you move up or higher in elevation for the reasons we just discussed. And then as it crests over the ridge, we get a deceleration regime as that wind sort of gets to expand over a larger volume. So this is like the analogy of being at a stream where you go from a really fast, narrow region and then it opens up into a wide channel. And so what you get is deposition of the snow that was picked up in the acceleration region and redeposited in the deceleration region. And so you have two different types of terrain where you're seeing acceleration and deceleration regions. And so one consequence of that are these things called cornices, where you have wind that is accelerating as the wind is moving up the surface of this ridge, picking up snow from this side. We call this the windward side of this peak or ridge, and then slowing down or decelerating on this side, and then we call this leeward or lee zone deposition on this side, and we end up getting these interesting shapes or depositions called cornices. The anatomy of cornice, it looks like this. So on the windward side we have the root that sort of anchors the cornice to the ridge, and then we have the roof, the top of that cornice, we have the face, and then we have the scarp. And on the right, I have some data that's a little old now, but I think it illustrates it nicely because it shows you the root, the roof, the face, and the scarp of that cornice, and then it shows you three measured properties of the snow grains. It shows you the diameter, the density with the scale here, and then the hardness of that snowpack by each of these four regions. And so pause the video here and see if you can come up with a hypothesis to this question, which are, what conclusions can we draw about the density, grain size, and hardness of a cornice based on these four different regions, and what you know about the wind direction and the anatomy of one of these cornices. Okay, so some things that we can take away from this is that the root is typically harder and denser, and we see that in the density data here. So we have a higher density, and we have an increased hardness in the root portion of the cornice. And that's because it's being slammed or packed in by the wind. So as those crystals are abraded and rounded, they then get consistently impacted into the root itself, such that no more can be transported or lifted. And then the grains that are suspended and moved over the ridge into the face and the scarp region, those typically are smaller grains because those are the things that have traveled a longer distance and saltated and bounced their way up over this ridge. As these things are hopping or saltating up and over this ridge, each time they have an impact from another particle, they're likely fracturing and getting smaller and smaller. So we get smaller grains down here in the leeward side, in the scarp, but we often have softer and less dense snow over here, and that's because all of the snow over here, even though it's been abraded as it came up over the crest of the ridge, it's not subject to the constant force of the wind compacting that into that dense layer. And so it's potentially counterintuitive, but it's interesting to sort of dissect the origin of the different grain types and sizes as a function of this cornice, which has pretty significant implications for the propensity for avalanches on a slope like this that's under a cornice. So the actual transport of snow is complicated, as I'd mentioned, and wind direction, the speed, the terrain, they all contribute to defining where the snow is going to distribute. And typically what we see are lee zone deposition, so that's deposition on the leeward side of ridges. We get cross-loading, and so these come from your Avalanche Handbook, the 3rd edition. So what you're seeing here is wind coming from the prevailing side, so that's winds out of the west coming over the ridge, decelerating and depositing in this gully here, and then simultaneously you're getting a cross-loading effect. So as wind shifts or the local wind microclimate blows across this gully, then you're getting acceleration for the same reason, where wind moves up over this small ridge and then decelerates and deposits that snow down in the gully. That's the cross-loading effect here. In the image to the right, you're seeing that exact effect, right? Each of these ridges is fairly barren, and then within the ridge, what we'd consider the lee side of each of these small ridges down in the gully, that's loaded with snow. And you could think about the size of the grains and the density of that snowpack in the similar justification that we talked about with the previous slide. One more point that I wanted to make is that just because the general wind vector is potentially prevailing coming out of the west doesn't mean that you can look at terrain and model that terrain and assume that the wind is moving from the west to the east in all of those different terrain features. And this is a really nice image of some recent data where some folks modeled the transport and the individual wind vectors as a function of the sort of large net wind vector. So you can see that the net wind vector was prevailing from west to east at 18 meters per second. So that's really high wind speeds. But within all of this complex terrain, here you have a gully, here you have a ridge, you have sort of a bowl feature here at the base of a peak. You can see completely different wind patterns, velocities and directions as a function of where exactly those features lie relative to the net wind vector. And so that gives rise to some complex loading of slopes, which can totally change the nature of the snowpack, especially if you go and you dig a pit and you start to analyze and you say, I don't really understand why I'm getting these really small rounded grains. That's when you start to consider what are the wind effects, and am I seeing any effects of wind deposition on the snow and the snow metamorphism.